Semester 2 final exam review. I have a few questions on here, over 20 some. If you don't need to watch the whole video, please fast forward through to the sections or the parts that you need to watch. Again, this is only a review. Hopefully none of this information is new to you and will be beneficial. So again, if you need to fast forward, please do so. I believe that everything that's on this review or study guide will help you on the final exam. Here we go. Question number 1 says, write and balance a complete chemical equation for the combustion of butane gas. One of the things you want to make sure you remember are the 5 different types of reactions that you were taught at the beginning of the semester. Again, the 5 types real quickly. A combustion reaction where you have carbon, hydrogen, sometimes oxygen. And again, what I'm doing is I'm putting just X, Y, and Z here because again, it's a generic equation. Reacting with oxygen will always form carbon dioxide and water. So make sure that you know that that represents a combustion reaction. The other type that we had was a synthesis reaction. And what happened there was you took A plus B and you formed one single compound, where A and B represented some element all by itself. Decomposition was the third type that we talked about, and decomposition reaction is the opposite of this reaction, where you take a compound and you break it apart into its individual elements. So that's a decomposition reaction. So we have a combustion reaction, a synthesis reaction, and a decomposition. There were 2 other types of reactions. Let me write those. Those 2 other types of reactions were a single replacement reaction. A single replacement reaction where if we have something standing all by itself, and we're going to call that a metal, and it's trying to react with a compound. So you have a single element reacting with a compound, which we'll call BC. And remember that the first thing written is always a metal, the second thing written is always a non-metal. So we always write the more metallic element first. So if A is a metal, A is going to try to kick B out, and then on the other side of the reaction, you'll have A is now with C, and B is all by itself. Now remember, you get to use the tables. So the tables that you would use here is a single replacement table, where you have the metals on the left and the non-metals on the right. So if we were going back and we said, okay, well now A is a non-metal, okay? So if A is a non-metal, what that means is that A is going to try to replace C in this case. And if A is a non-metal, remember non-metals can only replace other non-metals, metals can only replace metals. So in this case, if A were a non-metal, let's go ahead and write that, non-metal, then on the product side, we would not have this, but we would still have B as our metal, and A would be taking the place of C, and C would be kicked out, so we would have this reaction. So again, you have to, when you notice that you have a single replacement type reaction, you want to look at the thing that's by itself, the element that's by itself, and ask yourself, is that a metal or a non-metal? To refresh your memory on that, when you look at your periodic table, okay, remember that the periodic table is mostly made up of metals. The metals are on this side of the periodic table. The non-metals are right here. These are your non-metals. And more specifically, we're not going to be looking at the noble gases to determine that, but if you look at your non-metal triangle and you put a dot in the middle of the carbon, a dot in the middle of the fluorine, and a dot in the middle of the iodine, and you connect that, that's your non-metal triangle. In other words, these are all the non-metals that will be actively involved with the reactions that we're associated with. Now also keep in mind, hydrogen acts as both a metal and a non-metal. So when hydrogen is only with these guys, we're going to say hydrogen's a non-metal. So yeah, we'll leave it at that, and that's more of an organic type thing. So make sure that you know what metals and non-metals are and where they're at on the periodic table. Okay. The last type of reaction is a double replacement reaction. And a double replacement reaction involves 2 compounds. So a double replacement reaction has this generic equation where we have A, B reacting with, we'll say, X and Y. So what's going to happen here is the metals will switch. In other words, this is our swingers reaction. Partners are going to switch. The reaction will take place, but then we have to go to a chart or a table and look at some more information. So on the product side, you will actually have A with Y. Remember, write your metals first, and then you'll have X with B. Again, write your metals first. Then what we have to do is we have to check and see, is there a precipitate being formed, or something that is not soluble in water? And we'll only talk about water as our only solution that we'll react with. And you'll have a table that looks like this. So again, you'll have this table to your access, and you should remember how to use that. So if it's not soluble, you have a precipitate. If it's soluble, it looks the same as when you started. You started off clear, it finishes clear. No reaction for that compound. And again, remember that you have to have at least one not soluble within the reaction for there to be a reaction. Okay? So those are the 5 different types of reactions that you're responsible for. What's this question asking for? That's asking for you to write and balance a combustion reaction. So again, the combustion reaction involves a hydrocarbon, something with carbon and hydrogen reacting with oxygen, forming carbon dioxide and water. So in this case here, we have our hydrocarbon, which is C4H10. It will react with oxygen, and we'll always say that oxygens are excess, and you remember what that means. And we'll form carbon dioxide and water. So the question wants you to balance, so we already wrote it, so you know that whatever your hydrocarbon is, reacting with oxygen, carbon dioxide and water are always formed. So let's go ahead and balance these things out. So if you need to do it the inventory method again, nothing wrong with that. So I'm not going to do it, I'm going to actually speed things up. You can do the inventory method if you need to. So I'm going to start with the hydrogen. Actually, yeah, I'm going to start with the hydrogen. So hydrogen, I have 10. If I want to get 10 hydrogens over here, I'm going to need to put a 5 there. But remember, it's not a very good idea to place an odd number in front of the water. Why? Because if you do that, that gives you an odd number of oxygen on the product side, and there's no way to get an odd number on the left side or the reactant side. So actually showing that is a bad idea. 5 is a good value, but we want an even version of 5. So go ahead and double it. So say to yourself, okay, well, 5 is a great number, but I'm going to double that. So now I've got 20 hydrogen, so I need 20 hydrogen over here. So let's put a 2 there. All right, so my hydrogens are balanced. Now let's balance the carbons. So the carbons, we have 8 here and currently 1 there. Put an 8 there. Now I have 8 carbons on both sides. So now my carbons and my hydrogens are balanced. Last thing you want to do is balance the oxygen. So here I have 8 times 2, which is 16, plus 10 times 1, which is 10. So 16 plus 10 is 26. So I have 26 oxygens on this side, and currently I have 2. But I need a coefficient in front of here to represent a total of 26 hydrogen. So I would put a 13 there. So this is my complete balanced reaction for combustion. Let's look at number 2. Number 2 says write and balance a complete chemical equation for a single replacement reaction of calcium metal with aluminum nitrate. Now we talked about the 5 different types. So single replacement reaction. So in this case here we have single replacement of calcium metal, which is Ca, and it's going to react with aluminum nitrate. Now aluminum nitrate, that's aluminum nitrate that ends in ATE. That means you got a polyatomic. Remember your 10 polyatomics. So nitrate is NO3, and let's make sure we balance our charges. So aluminum has a +3 charge. How do I know that? Because I have the periodic table right in front of me, and it's in group 3A. Aluminum has a +3 charge. Keep that periodic table in front of it. You're going to need it, unless you have that thing memorized. I don't, and I don't expect you to. All right, nitrate is a -1 charge. If you don't remember that, get your flashcards out, memorize that. So that means we need 3 of these. We currently only have 1. Yes, I see a 3 there, but that is the polyatomic NO3. So what that means is you need to balance and put a 3 there. All right, so since this is a single replacement reaction, let's check our sheet to make sure that this will actually take place. So go back to your single replacement reaction sheet. All right, so again, the reaction was calcium and aluminum. So find calcium. Calcium is right here, and calcium's all by itself. Aluminum is right there. And remember that the thing that is standing by itself and trying to replace something in the compound has to be listed higher than the thing it's trying to replace. So same thing with the nonmetals. Fluorine can replace everybody, iodine can replace nobody. So in this case here, calcium is the thing standing alone, so that means that calcium will come in here and kick the aluminum out. So the aluminum's going to go out of that compound. Calcium's going to adhere to this. So now what we're going to have is we will have calcium nitrate, and all by itself will be aluminum. So we will see the calcium metal disappear. Okay, we have a solid calcium metal. It will disappear. It actually will react with the nitrate and actually ionize out. You will see aluminum, not present initially, start to come out of solution because of this is a nice little redox reaction too. Remember that. All right, so let's balance charges on the right hand side because we need to balance. Calcium has a +2 charge. How do you know that? Well, calcium is in group 2A. So there's calcium, group 2A. And we know nitrate's a -1, so what that means is I need 2 of these nitrates. I'm going to go ahead and make that a different color. So now that we have that balanced, we know the reaction takes place, let's balance the number of atoms. Start ugly early. I have 3 nitrates here, 2 here. So that means that I need to use a different color. So let's go with red. So that means I need a 3 there. So I have 6 nitrates here, so I need to get a 2 there. So my nitrates are balanced. I have 3 calcium on the right, therefore I need to put a 3 in front of the calcium there. Now the last thing I need to do is balance my aluminum. I have 2 here, put a 2 there, and I am now balanced. Okay? All right, number 2. Let's look at number 3. Okay. Number 3 asks, write and balance a complete chemical equation and determine the precipitate, the not soluble product, for a double replacement reaction of lead-2 nitrate and lithium phosphate. Now again, that means that we will be using this table over here. Or I'm sorry, not this table, but we'll be looking at the double replacement table. So we'll come back to that in a second. So let's see here. Let's start off with the things that we start with. So we have lead-2 nitrate. So lead and nitrate. And since the Roman numeral 2 is there, that means that lead has a +2 charge. Nitrate, I like using nitrate. So it's a -1, that means I need 2 of those. And it's reacting with lithium phosphate, so lithium, Li, and phosphate, again, ends in ATE, you're looking at a polyatomic. So phosphate, looks like that. Let's get our charges. Lithium +1, phosphate -3. That means I need 3 lithiums. Very good. All right, I can't move those. I can't. All right, so again, this is a double replacement reaction, which simply states that the metals are going to switch places. So let's go ahead and predict what our products are now. So on this side, we'll have the lead with the phosphate, and we'll come back and balance that. And we'll have lithium with nitrate. Okay. All right, so let's balance charges here. So we know that the lead is a +2, given. Phosphate, -3. So that means I need, let's see here, 3 leads. This is going to look pretty bad. So Pb3, parentheses, PO4, parentheses, 2. So now I've got the same number of lead on both sides. And I now have 2 phosphates. So let me put a 2 there. So now my phosphates are balanced. Now I have how many lithiums? 2 times 3, which is 6. Put a 6 there, so now I have 6 lithium, 6 nitrate. I only have 2 over here, but again, nicely, I have a 3 by the lead. So to get 6 nitrates, I need to put a 3 here, which gives me 3 lead. So our equation's balanced. Let's check the chart and see who forms our PPT. And where are you? So let's look at the first one here, sorry. So let's look at lithium nitrate, since it's right at the top here. Nitrate, if it's with any positive ion, it is soluble. Soluble means clear, does not form a precipitate. And then the other one was lead phosphate, so we'll come down here to the bottom. Phosphate, come across, is lead an alkali ion or ammonium? It is not. Go to the second row. Lead is any other positive ion, therefore it is not soluble. So that means that we do have a PPT, or more importantly, we have a reaction. So there we have our completed balanced equation. Number 4. Number 4 says, or asks, explain oxidation reduction and give an example of a redox problem. Probably an interesting question here. Oxidation and reduction. Oxidation and reduction involve an exchange of electrons. And we actually were looking at that exchange of electrons back here in question number 2. You may not have realized it, and actually I'll revisit this problem for our example. But when we talk about oxidation, remember the statement that I gave that says, Leo says grr. Remember that? Leo says grr. And what that means is losing or lose electrons. If I can run out of room, lose electrons is oxidation. Okay, so whenever an element becomes more positive, because it's losing negative charges, it's being oxidized. And then gaining the electrons means that it's being reduced. Okay, so if I gain more electrons, I'm going to become more negative. So let's take a look at this example back here where I'm looking at the calcium. Calcium right here, and I didn't write a charge above it because I wasn't balancing it. But what is calcium's charge all by itself? Very good. It has no charge. It doesn't have a charge until it's with something else. Kind of like when somebody's all by themselves, they shouldn't be excited. They should get excited or have a charge when they're with somebody else. Nice analogy. So in this case, calcium has no charge. And what is happening is as we go from here to here, calcium does have a +2 charge. Why did it do that? Because it lost 2 electrons. So when that calcium lost 2 electrons, it went from no charge to a +2 charge by losing electrons. Pretty cool. The aluminum over here has a +3 charge. What's the charge on the aluminum here? That's right, nothing, 0. So what happened here was that the aluminum that had a +3 charge, to get to no charge, had to gain 3 electrons. Has +3, needs to gain 3 negative charges to have no charge. Now, if I were asking you to balance the redox equation, we would multiply the bottom by 2 and the top by 3 because we never ever see electrons in an overall balanced equation. So when you look at it and you say, okay, well that kind of makes sense because if actually just multiply. Since I have 2 electrons here, I would need 3 there and 2 here. And that means that the electrons are actually being canceled out in this overall balanced equation. How many calcium ions do I have in this reaction? 3. So it was already balanced out that way. How many aluminums should I have? 2. And I had the 2. So the electrons help us in not only balancing the chemical formula or the equation, but also balancing the formulas itself. So this is a pretty neat little reaction, and that's what redox is. Losing electrons, actually let's go back to it. So losing electrons is oxidation. Gaining the electrons is reduction. Number 5. Determine the oxidation or the charges, the potential charge for each of the elements in the molecule F2CO3 parentheses 3. Now we did this earlier on. All right, so what we want to do is we want to find the charge, the potential charge or oxidation number for each one of these elements. So the way that I like showing it is I'm going to stack them. I'm going to put the iron right here, I'm going to put the carbon right here, I'm going to put the oxygen right here. Now the overall charge for this entire molecule is 0. How do I know that? Because I didn't write a charge up there. So if there's no charge, it has no charge. So that's kind of an easy rule to live by. So that means that this whole thing has an overall charge of 0. Now I do want to count how many atoms I have. So iron, I actually have 2 of those. The carbon, I have 1 times 3. And oxygen, I have 3 times 3, which is 9. We know from the periodic table that oxygen always has a -2 charge. So we can always start with oxygen, which is kind of cool. So oxygen has a -2 charge. Let's find out what that total charge exhibited by all the oxygens happen to be. So 9 times -2 is a -18. All right, so now we kind of hit a wall here because iron has multiple charges. It can be a 2 or 3. Carbon has actually like 3 different charges. It's going to be +2, -2, -4. I'm sorry, +4. So really looking at the periodic table isn't going to be that helpful for us in this case here. So actually, scoot it on over. So the carbon can be +4, -4, or +2. And then the iron, which is right here, can either be 2 or 3. So we have to figure out, well, which one is it? Here's what I suggest. You're going to let these help you tell what the charge is on the other thing. So if I'm looking at 2 irons, that must mean that each one of these has a -2 charge. And it does. It's carbonate. If I look at this, that means that each one of these has a +3 charge. And it does. So when I actually treat these subscripts as multipliers, the whole compound has no charge. So the last thing you want to do is check and see if the charges actually make sense. Well, iron has a +3 charge. Is that a potential charge? Actually, let's blow that up a little bit and let's see. So iron can either be a 2 or a 3 charge. Looking good. And then what do we have for the carbon over here? Actually, oh, hold on. We got to write that down first. So let's get our carbon as a +3 charge. So that means we have 2 times that. So +6. Now, what's neat about this problem is we know what the whole charge on the carbonate is, but we don't know what the individual charge on the carbon is. There's a couple ways you can find it out. But since it's the only element remaining, this is the easiest way to go about it. And here's what we do. We're actually going to work backward. So now we know that we have a +6 charge for our iron, we have a -18 charge for our oxygen. So we need to find out what is that mystery value right there that's going to give us a total charge or a total value of 0. So in other words, I have +6 -18. This number has to be added to all of these to equal 0. What would you guess that value would be? Exactly, a +12. In other words, 12 plus 6 equals a +18. -18 is 0. Now we work backward. So we know we have a +12 charge, but we have to divide that by 3, which means that we now have a +4 charge. So each of the carbons in this compound has a +4 charge. Let's double check and make sure that it's actually a legal charge. So we come over here, scoot it on up, and carbon again can be either +4, -4, or +2. +4 is a valid charge. We like that. So the oxidation numbers are these values that I have in the box. So if I were to ask on the final exam, looking at this compound, what is the oxidation number for carbon? You would say +4, not +12. +12 is total charge that all the carbons are exhibiting. So +4 is the oxidation number for carbon, -2 is the oxidation for each oxygen, and +3 is the charge on each iron, or the oxidation numbers. Number 6, calculate the number of moles of sodium chloride in a 500 gram sample of sodium chloride. Now recall, since we're looking for moles, our pathway that we want to do our stoichiometry or our dimensional analysis. So we're moving from writing chemical equations into not necessarily stoichiometry, but doing some mole values. The sequence, which should be very helpful and very easy to remember, is this: that if you start off with, say, something like kilograms, milligrams, nanograms, whatever has a prefix in front of the grams, you want to take all those and convert them into grams. Now, why would you want to convert those to grams? Well, it just so happens that the periodic table, these values down here, even though they're atomic mass units, if I were to look at, say, 1 mole of these particles, each one of these elements, that is how many grams that mass happens to be here on planet Earth. So I would convert whatever's given to me into grams. From there, I would convert those grams into moles. Why? Because that's what the periodic table symbolizes. Everything on here has a molar mass. And all of these things actually have 6.02, well, that's a big fat number. All of these things actually have 6.02 times 10 to the 23 particles for every mole. So if I want to find out how many, or what the mass is for 6.02 times 10 to the 23 atoms of chlorine, I come over here and I check my mass, 35.45. Now, this is, again, the average of all the isotopes. So there are different atoms, and again, that's what all the decimals represent, different atoms that have different numbers of neutrons. That's first semester stuff. You already remember that, so we don't need to review that. So once you have your value converted into moles, then we can either convert that into molecules, and then maybe even go a step further and convert it into atoms. So molecules and atoms. Okay, so that's the sequence. Now what's beautiful about this sequence is we can also move in reverse on this sequence. So once you have that sequence in play, okay, say if I gave you a certain number of atoms of some sample, you can convert those atoms into molecules, those molecules into moles, those moles into grams, those grams into anything else. Pretty cool. And the only time that we use this value, I don't know why I keep trying to move that, but anytime that we try to use Avogadro's number, it's when we go from moles to molecules. And anytime that you have moles within the problem, not starting, not finishing, but starting with it, it's always going to have a value of 1 within the problem. And then molecules, we would say that in 1 mole, we have that certain number of molecules. So let's work this problem out. So it says calculate the number of moles of sodium chloride in a 500 gram sample of sodium chloride. So we start here, and we're only going here, so it's a 1-step deal. So don't try to do something fancy and like convert the grams into kilograms and then convert it in. Just keep it simple. This is a one-directional street. So you find out where you're going to start based on the question, and then you move in one direction. So we're not going to start at grams and move the moles to find out how many kilograms. Don't do it. Be efficient. Be efficient. So we have our 500 grams of sodium chloride. How do we know that? Because I gave it to you. And we're going to convert that into moles. So 1 mole of sodium chloride. Your molar masses, again, from your periodic table, they're on there for you. So sodium chloride's on the other side, it's 22.99. Chlorine's 35.45. So we'll put our 22.99 plus our 35.45 grams. And let's get a mass for that. And that equals 58.44 grams. And again, that's 1 mole, or 6.02 times 10 to the 23 molecules of sodium chloride. So take 500 divided by 58.44, 8.56 moles of sodium chloride is in that sample. And my calculator says 8.55578,371. But again, make sure you're showing 3 sig figs. Number 7 says calculate the number of sodium chloride molecules in a 500 gram sample of sodium chloride. All right, so really what we're doing here is we're just simply going one additional step. And what's cool about this is we already found our number of moles, but I'll go ahead and show the whole sequence. But the question wants to know, okay, the number of molecules in a 500 gram sample. So again, we're starting here because the question told us you have 500 grams. So we're going to convert the grams into moles, convert the moles into molecules. So this is a two-step process. So let's go ahead and do that. So we'll start off with our 500 grams of sodium chloride. And again, convert the grams into moles. So 1 mole of sodium chloride. How convenient, there's the mass, 58.44. And now, remember, if it's not the unit you're looking for, we're sliding it diagonally. So the grams have already canceled out at this point. So now we need to get rid of the unit moles and get molecules. So slide it. So 1 mole of sodium chloride. And notice that whenever you're working with moles within the problem, not starting with it, within the problem, it's always a value of 1. Always a value of 1. And mass is never 1 gram. So don't ever do something weird by saying, okay, that you have some number of moles, but you have 1 gram as your mass. Ugh, don't do that. All right, so getting rid of the unit moles, now we're going to molecules. That's when we get to use the 6.02 times 10 to the 23 molecules. Okay. Now, if the question wanted to know how many atoms we had, we would go one more step and convert those molecules into atoms. If you were to do that, you would place 1 molecule on the bottom in your next step, and then you'd say, well, how many atoms are in 1 molecule of sodium chloride? Well, in 1 molecule of sodium chloride, there happens to be 2, 1 sodium, 1 chlorine, and then you'd multiply that all out. So let's get a value for this. So 5.15 times 10 to the positive 24, and again, that's molecules. Awesome. Number 8, calculate the percent composition of oxygen in a 500 gram sample of calcium nitrate. Percent composition of oxygen in a 500 gram sample of calcium nitrate. Now, the beautiful thing about this is we don't care about whatever size sample we have of this. That is kind of a distractor. If we were to ignore this mass right here, can we still answer the question? You better believe it, because it tells us that we have oxygen and we have our compound. So it doesn't matter if I have a 1 gram sample, a 500 gram sample, a 5,000 gram sample, because the percent will always be the same. So what we need to do first is find out what the molecular mass of the calcium nitrate is. So calcium nitrate, okay. Calcium, we have 1 of those, which is 40.08 grams. How did I get that value? It's on the periodic table. We got to scoot it on over. So calcium down here, 40.08. Okay, let's get you back. And we have 1 of those. We also have 2 nitrogens. So 2 times 14.01. Plus we have 6 oxygens. So this whole thing weighs equals 164, and I don't want to round this value at all, 164.1 grams. And that's 164.1 grams for every mole of that. All right, so now to find the percent of our oxygen, okay, now oxygen in a compound is just O. Don't sit here and say, oh, it's the oxygen. No, it's not the oxygen in the air. It's just the percent of oxygen. So we want to find out, okay, which of these masses represents the oxygen? Well, we have 6 times our oxygen. So really, it's 6 times 16 divided by the total mass, which is 164.1 grams. And then we would multiply that by 100 to get our percent. So let's do that. And hopefully you're using your answer buttons here. You're not retyping all this. You want to be super efficient with your calculator, especially as you move on to AP Chemistry. The calculator says that I have a percent of 58.5, I believe. 58.5? Yeah, 58.5% of calcium nitrate is made up of oxygen. Pretty cool. All right, So again, this distractor of the 500 grams doesn't change anything, but I'm willing to bet that that might throw a few of you off, so be careful. Number 9. Determine the empirical formula for a compound containing, and in this order, 14.775% lithium, 34.128% sulfur, and 51.096% oxygen. Now, I didn't give you a mass amount like I did on the last one, but if I did, ignore the mass amount. Strictly look at these percentages and pretend that you have a 100 gram sample. I think actually if you were to count up or add up all these values, it'd be 99.999 grams, but we're going to pretend it's 100 grams. So change those percentages into grams, and let's find out how many moles. Because again, when you look at the periodic table, even though the periodic table has all these nice masses, 1 mole of one thing doesn't weigh the same as another. However, if I have 6.94 grams of lithium and 47.9 grams of titanium, I have the same number of particles because I have 1 mole of each. So that's why we always want to change what's given percentage-wise into grams and then into moles, because moles is the equalizer. So let's do that. So we have our 14.775 grams of lithium, and 1 mole of that is equal to 6.94? Yeah, 6.94 grams. We'll come back and get that. And then we'll look at, and I need to write smaller, so 34, let's change colors, that'll probably help a little too. 34.128 grams of sulfur, and 1 mole of sulfur actually has a molar mass of 32.06 grams. Yeah, we'll come back and get that. And then we have 51.096 grams of oxygen, and 1 mole of oxygen. And again, notice how I'm not writing the subscripts here, because again, it's as you see it on the periodic table. It's 16. So let's get some values there. Here are my values. So lithium, I have 2.12, and I don't want to round this. 12896 moles. My sulfur, I have 1.0645 moles. That's what my calculator is telling me. And my oxygen, I have 3.1935 moles. So what I want to do is, now I want to look at my number of moles. I can't get a ratio from that. So what I want to do is find the smallest number of moles and multiply everybody by that. So it looks like my sulfur is the smallest value. So I'm going to multiply all those by this value. I can do that in my head. That's a 1. 1.0645. Looking at that, I'm going to say that's 2. 2.12 divided by 1.06. That is a 2. That's very, very close. And then looking over here, 1.06. And again, I know that 3 divided by 1 is 3. 19 divided by 6, that's very, very close to 3. So this is a 3. And if you go through there and look at that, you're going to find out that those ratios are very, very close. That might be like a 2.99 or a 3.000 with some numbers behind it. So once we have our ratio, now we can put this together and say, okay, well, this is lithium. I have lithium, 2 of those. Sulfur, I have 1 of those. Oxygen, I have 3 of those. So Li2, SO3. And then if you have a metal with a non-metal, you can check charges. So when we look at the lithium, you're like, oh yeah, lithium's got a +1 charge, and there's 2 of those. SO3 is not one of our polyatomics, but we did talk about what happened if you removed an oxygen. That's not sulfate, but that's sulfite. And sulfite has a -2 charge. So this baby's balanced as written. Okay, so again, empirical formulas, you'll be given a percentage, change that percent into grams, find out how many moles by looking at the periodic table to find out what your molar masses are, and don't make the mistake. Don't say, oh, oxygen's O2. Don't do that. That's a bad deal to do. Okay? So, and then Once you have your number of moles, find the value that's the smallest number of moles and divide everybody by that. Number 10. Determine the number of moles of oxygen gas that must react with excess hydrogen gas to produce 500 grams of gaseous water. So now we're moving forward into stoichiometry. You know you have a stoichiometry problem when you are given more than one type of reactant. Pretty cool. So first one, step one, always write a balanced equation. So step one is write a balanced equation. So determine the number of moles of oxygen gas. So oxygen gas that must react with hydrogen gas. And again, that word right there is a big heads up. Hey, react, I've got stoichiometry going on here. To produce 500 grams of water. Okay, so let's write down what we know before we do step one. So oxygen, determine, so we're looking for the question mark there, determine the number of moles, and then excess hydrogen, hey, limiting reactant type problem, but we know who the limiting reactant is. It's not the oxygen, because this is excess. And then it says that we have 500 grams of our water. So that is given to us. So now let's balance. So let's see here. We have two hydrogens. That looks nice for now. Oxygen, we have one. Oxygen, we have two over here. So that means that we need to put at least a 2 here. By putting the 2 there, now we have 4 hydrogen, so I need to put a 2 there. Step one, write a balanced equation. Step two, take what's given to you. This is not given, this is the question. 500 grams is given, so we want to take what's given and convert that into moles. So 500 grams of water, and again, you work with water enough, you're going to know, yeah, water has a molar mass of 18.016, so convert this into moles, so 18.016 grams, and again, got those values from the periodic table. So this is all step two, changing what was given into moles. So I took my grams, converted it into moles. Step three is I'm going to use my mole ratio, and my mole ratio comes from my balanced equation. So I have moles of water here, so I want to move my unit moles of water down here, and I'm looking for, I have my mole, I have my moles of water here, and I'm looking for my moles of oxygen. So I'm going to put moles of oxygen right there. So once I have those put into place, now I go back to my balanced equation. I say, okay, well, what coefficients do I have? Those are the values that I'm going to plug into my equation. So water has a 2 as our coefficient, and oxygen has a 1. So when looking at this, that is step 3, which is use the mole ratio. In other words, to get rid of the unit we started with, moles of water, and get to the unit that we're looking for, in this case, moles of oxygen. Even if these coefficients are the same, we still have to show the step because the units are not the same. Step 4 is to convert what we have now into the desired unit. Well, our desired unit, in this case, is moles, so we're done. If I were to find out how many grams of oxygen, I would go one more step. I put my moles of oxygen down here and my molar mass for oxygen on top, and then do the calculation. But luckily, the question's not asking that. So let's do this calculation real quick, and I get a value of 13.9 moles. And again, that's 13.9 moles of oxygen gas is needed to react with all the hydrogen I have, or the excess hydrogen, to produce 500 grams of water. Number 11. When 500 grams of calcium nitrate reacts with excess lithium carbonate, how many grams of the precipitate is formed in this reaction? Looks like we have another stoichiometry problem. And again, it's not a limiting reactant problem because it tells us who the excess is. So step 1, write a balanced equation. Very good. So calcium nitrate, and I'm going to go ahead and just write this out because you guys are experts at writing out formulas. So calcium nitrate and lithium carbonate. Lithium has a +1, carbonate a -2. That means we need 2 of those. And in this reaction, it's a double replacement reaction. Very good. So that means calcium is going to be with carbonate, and the lithium is going to be with the nitrate. So lithium and nitrate, and then calcium with carbonate. Always write the metal first. All right. And before we balance, let's write down what we know. So we have 500 grams of calcium nitrate. So we have 500 grams of calcium nitrate. And it wants to know how many grams of the precipitate is formed. Ooh. Now we have to go to the table and find out which of these forms a PPT, or the precipitate. So before I can put a question mark above that, I need to find out who is going to form a precipitate. So looking at this, lithium nitrate. So we'll look at the lithium, or the nitrate. Nitrate again, any positive ion? Soluble. Soluble means clear. Nothing's happening there. So hopefully the other one is, or else we have a no reaction, and that would be awful, because we wouldn't want to have a no reaction on this. Calcium carbonate. So we look at the carbonate, find carbonate, carbonate. Down here, we come across, is calcium an alkali ion? No, it's an alkali metal. So we go to the next row, is calcium any other positive ion? Yes, not soluble. So that means that our PPT is right here. So the question wants to know how many grams of our PPT. All right, so now we have the information. Let's go through. Step one. Write a balanced equation. Well, our formulas are good because they're all balanced charge-wise. So let's see here. Let's go ugly, ugly, ugly. Looks like this is our ugly one. So we have 2 nitrates here. That means we need to put a 2 there. You gotta sneeze. So once we have 2 nitrates, now we have 2 lithium. We have 2 lithium. Ooh, carbonate. We have 1. 1 carbonate. Calcium, we have 1. Calcium, we have 1. This is balanced by putting that 1, 2 there. All right, so step 1's done. Step 2, change what's given into moles. So let's take our 500 grams of calcium nitrate, and let's convert that into moles. A mole of calcium nitrate. And the molar mass for calcium nitrate, I'm just going to type that up here real quick. So 164.1 grams. Okay. So that again is all step 2. Step 3, let's use the mole ratio. So we want to get rid of moles of calcium nitrate. In this case, we're going to go to moles of calcium carbonate. And if I would have designed this problem better, we'd have coefficients that weren't 1. So I apologize for that. But again, we still need to show this step because the units do change. And then we're looking for grams. So that means we're going to move the moles of calcium carbonate down. Calcium carbonate. And then we need to find the molar mass for that. Let me pull that up real quick. 100.09 grams. All right, so let's find out exactly how much of this we have. So again, breaking this down. This is that's step 1, writing a balanced equation. Step 2, changing what was given into moles is step 2. Step 3 is using the mole ratio, getting rid of the moles of the calcium nitrate to get moles of what we're looking for. Step 4 is converting to the desired unit. And in this case, we want to get rid of the moles of calcium carbonate and get grams of calcium carbonate. So let's calculate and find out how many grams of calcium carbonate is formed in this reaction. There are 305 grams of calcium carbonate formed in this reaction. Number 12, describe the limiting reactant in a chemical reaction. Now what's nice about up till this point, all of the questions that I've been asking have not had a limiting reactant. But I'll go back and look at a couple of these questions here. Now, what a limiting reactant is simply this. It's something that we start with that runs out first or is consumed completely before the other reactant or reactants have had a chance to be consumed. Now, in these examples here, I had given you the example that we're looking at excess lithium carbonate, and then I think in the other one we had excess hydrogen gas. So what that's telling everybody is that, hey, the thing that we're looking at, or the other reactant, is actually the limiting reactant. In other words, it will be totally consumed before the excess is. And once that limiting reactant is totally consumed, the reaction is stopped. It will no longer be able to produce any of the product if you don't have any one of these reactants. So that is what a limiting reactant is. So I guess what we could put on here, LR is one of the, and I'm going to say one of the entities. In other words, could be an atom, could be a molecule, could be an ion, it could be something. One of the entities that you begin with, so that's a reactant, begin with, and is totally consumed, actually is completely consumed. In other words, completely used up before the other reactant or reactants. Okay. All right. Number 12. You had a reaction in the lab and obtained a mass of 500 grams for your only product, copper metal, Cu. And according to your calculations, your correct stoichiometry calculation, you should have collected 650 grams of copper metal. What is the percent yield and the percent error? And I put a here and on here. These are not the same thing. So when we talk about percent yield, let's look at that first one, percent yield. Percent yield is equal to what you recover in the lab divided by what your stoichiometry told you is going to be. So I'm going to put stoich. So what you recover in the lab divided by what you were supposed to get times 100. So that's your percent yield. The percent error, okay, is a totally different thing. So percent error is the absolute value of what you get in the lab minus, actually let's scoot that over, minus the true value. In other words, generally speaking, what we do is we can do a calculation, could also be a stoichiometry type deal. So the true value would represent the stoichiometry value. So we'll take our value minus the true value. If that gives you a negative sign, that's what the absolute value means, drop that negative. Then you will divide that by the true value and multiply that by 100. So by looking at these two equations, you can hopefully see that these two values would be entirely different. So let's see here. Let's try to do the percent yield. So it said that I obtained 500. I'm going to go 500 grams. And my stoichiometry said I was supposed to get 650. So I'll multiply that times 100. And let's get a number. So that's around, we'll say 76.9%. Okay, so that's our percent yield. Now, I guarantee you our percent error won't be anything like that. So the percent error, so in the lab, so my percent error, I will take my 500 grams and subtract it by what I should have obtained, which is 650. So that right there gives me 150 grams. And again, I'm going to drop the negative. Then I will divide that by 650 grams, so the true value. So 150 divided by 650 times 100. So let's do that. And that's a 23.1. 23.1%. And that looks pretty darn close to the difference of the percent yield and the percent error, which is something that we would hope to expect to achieve. So again, the percent yield is actually how much we get based on how much we collected divided by the amount that we should have received or collected. And then the percent error is the difference of these two divided by the total. Number 13, you fill a balloon with helium gas to a volume of 0.5 liters at a temperature of 23 degrees Celsius. And the pressure inside the balloon is recorded at 500 torr of pressure. Calculate the mass in grams of the helium being used. So what we have here, and actually let's identify them. So you have a balloon filled with helium, so that's helium is He, to a volume of 0.5. So I'm going to go ahead and actually do this. So my volume is 0.5 liters, and I really like that value because that is in our ideal gas constant units. At a temperature of 23, not happy with that one. So let's go ahead and add 273 to that, which is a very clean 296 Kelvin. Always change or convert your temperature into Kelvin scale. And the pressure inside was recorded at 500 torr pressure. So I'm going to go ahead and convert that into atmospheres. And there's a neat little conversion that you may have noticed, that 760 torr equals 1 atmosphere of pressure. And it wants us to calculate the mass in grams. Okay, so let me go ahead and get a couple of these values real quick. So 500 divided by, so that is 0.658. Okay, so I have my units here. So I have a half a liter, 296 Kelvin, 0.658 atmospheres of pressure. Now, I really like being able to change PV equals nRT into this equation here, where I have PV equals little m over big M RT. So if I'm calculating for the mass, what I'm really looking for is this. And I know my pressure right there, my volume right here, my molar mass, well, it's helium, so that's 4.00 grams per mole. My R is R, my T is my temperature. So all I have to do is rearrange this and plug these values in. So let me do that. PVM, and what I did was I multiplied the M on top, and now I'm going to divide the RT on the bottom. Okay, so put that back. So M gets multiplied, RT gets divided. Okay. And this all equals little m. I hope I can fit all that on there. So my pressure is 0.658 atmospheres. My volume is 0.5 liters. My molar mass is 4 grams. And again, I get that from the periodic table. 4 grams per mole, so I'll put the mole right there. My R, I'm using atmospheres, so 0.0821 atmosphere liter. I'm going to put that mole Kelvin right up here. I know it looks kind of ugly up there, but I'm running out of room. And then the temperature is 296. So 296 Kelvin. So let's cancel out any like terms. So atmospheres are gone. My liters are gone. My moles are gone. My Kelvin are gone. What unit remains? Grams. And whatever all that equals. So let's go ahead and get a value for that. And that equals a very small amount of mass. So 0.054, we'll say 1 grams of helium. So not very much. Not too bad. Okay? So again, make sure you convert your units if they're not in the same units as your R value. And again, remember, you have 2 different R's. You get to use atmospheres or kilopascals, whichever pressure you decide to convert to. Also, this conversion is on the back of your periodic table. So if you are like, ooh, where do you get that? I like that. You can use that. It's given to you. And then make sure that you have your units in the correct spot. And again, I've talked all year long about allow your units to talk to you. Grams is on top, the numerator, that's where I want it because that's what my mass is. If my grams are on the bottom, that means I have this whole equation flipped. So be sure that you're actually paying attention to your units when you actually go and solve for this. All right. Number 14. Describe the conditions at standard temperature and pressure. And it says, assume that you have 1 mole of a gas. Now, the nice thing about standard temperature and pressure, or also known as STP, is that for any gas, it doesn't matter what kind of gas it is, for any gas, if you have 1 mole of a gas at standard temperature and pressure, which means that this would be equal to my number of moles, that my temperature is at 273 Kelvin or 0 degrees Celsius, which we really don't want to have to talk about with gases. So 273 Kelvin, the pressure, our pressure is at 1 atmosphere. Pretty much what we're experiencing right now. It's a nice, beautiful, sunny day outside. So we have 1 atmosphere of pressure. And let's see here, and the volume. This is a really nice thing. If you have 1 mole of a gas at these two conditions, your volume for this gas is 22.4 liters. Now, you don't have to memorize that value, but it is nice to have, because if you are doing some stoichiometry and the conditions are at STP, you can say that for every 1 mole of gas, you have 22.4 liters, as long as the temperature and the pressure are under these conditions here. 15. Calculate the mass of 500 liters of carbon dioxide at STP. Well, looky there. So here, again, if I have 1 mole of gas, I can use this conversion as long as we're at STP, and we are. So we can do this calculation rather quickly. So I start with what I know, that's what's given. So I have 500 liters, and it wants you to calculate the gas for the carbon dioxide. But let's get this to moles first so that we can actually do some conversions. So 1 mole of any gas of CO2 under these conditions happens to be 22.4 liters. Units of liters cancel out, which is very nice. And then the last step is convert the moles into mass, which is grams. So move your moles down. So 1 mole of CO2. And the mass of that is 44.01. So we have the units that we're looking for. Let's go to our calculator. 982 grams of carbon dioxide. Pretty cool. Very simple. So as long as you know the conditions at STP, that makes this calculation go by very quickly. If you don't remember this conversion, then you can still plug it into PV equals nRT, where your volume is 500 liters, your pressure is 1 atmosphere, your temperature is at 273 Kelvin. You can rearrange the equation to plug in for little m and big M, and then get what you're looking for here. Number 16, determine which gas effuses the fastest. Okay, it's kind of like in a road race, or if you're racing against somebody. Generally speaking, those who are built smaller, and I'm talking about adults or young adults, those who are built smaller, in other words, not big football frames like myself, can generally run faster. So we're going to use the same premise here. We're looking for the gas that weighs the least. The lighter the gas, the faster that gas is, under the same conditions. As long as the temperature is the same, the lighter weight gas will move faster. So if we look at this, we just said that the carbon dioxide had a molar mass of around 44. The chlorine is around 70. The helium is around 4 grams. Xenon is really big, I'm not even going to look at it. And oxygen's around 32 grams. And again, this is that many grams per mole. So the helium is clearly the winner in this case. The lighter the gas at the same temperature, the faster it is. So your answer is helium. So lighter masses equals faster at the same temperature. Pretty cool. All right, number 17. Describe the terms solute and solvent. Solute is the thing that gets dissolved. So if we were looking, say, okay, at a container here, and we had, say, some water in there. The solute is the thing that is being placed in there. Okay, so the solute, actually in this case, is that guy. So the solute is the thing that is dissolved by the solvent. So the solvent is the thing that is doing the dissolving. So it's safe to say that a solvent is a liquid. The solute is a solid for all the examples that we use, but that's not the case in every single example. So probably the best thing to remember is the solute gets dissolved within the solvent. Okay. One other important thing about this is you have to make sure for this to take place, like dissolves like. In other words, if this is a polar compound or a polar solid, it has to be dissolved in a polar liquid. In other words, if this were nonpolar, this polar liquid would not dissociate or dissolve this substance. So remember, like dissolves like. And that's another reason for this guy here. So we have this oil and water mixture here. Oil on top, water on the bottom. They don't like each other. So when I try to move them around or get them next to each other, they're very upset. They do not want to be next to each other. So there is no solute and there is no solvent in this example here because they simply don't like each other. And if you were to shake this up, yeah, for a moment it would look like they're actually being mixed together, but they are definitely not being dissolved or reacting with each other in that regard. Okay. Number 18. Calculate the molarity for a solution containing 500 grams of sodium acetate, and you know your formula, in enough water so that the total volume is 5 liters. Okay. So remember, when we talk about molarity, molarity deals with the number of moles per liter. And again, it's moles of solute over liters of solvent. So very appropriate that we have that up there. So what we need to do is we need to change our grams of sodium acetate into moles. Then we need to change, well, how nice is that? Our solution actually into liters. Well, it's already in liters, so that's pretty cool. So we can say, okay, well, we have 5 liters of that. We could do this all in one step if you'd like. We can take our 500 grams of our sodium acetate, and let's see here, I want to change that into moles of sodium acetate, C2H3O2, and let's put the molar mass down there. Let me find that real quick, and that's 82.034. Okay, now looking at this, okay, these two things represent the same thing. Why? Because when the grams cancel out, what units remain? Moles divided by liters. So you can incorporate this all together if you need to. So let's find out what this value is. So that gives me a value of 1.22, and that's moles per liter. So 1.22 moles for every liter of the solution. Molarity is pretty simple. Now, there is another thing out there called molality. Now, molality is a little bit different. Okay, it's little m number 1, and it represents the number of moles per kilogram of your solution. Now again, remember from the lecture where we were talking about how this Galilean thermometer is working, realize that even though we have the water in here, the mass of that water within the Galilean thermometer doesn't change. But as that liquid heats up and cools down, the volume of this liquid changes. So generally speaking, when we work with molalities, we're working with a liquid that's volume is changing ever so much. So we have to be able to know what the mass is whenever doing molality. And again, you only use molality for situations where you're looking at a freezing point depression or a boiling point elevation. So hopefully we'll have a couple of those here in a few minutes. Number 19, calculate the mass in grams of the solute sodium acetate when a solution has a total volume of 500 milliliters and a concentration of 3.33 molarity. If you know both the volume and the molarity of any solution, you always start with the volume. Now back here, we did not know both the volume and the molarity. We were actually calculating the molarity. That's why you see this, moles divided by liters. We had to find out how many moles we had. So if you know the volume and the molarity, then you start with the volume. If you don't know the molarity, you actually put the volume on the bottom. Keep that in order, okay? And remember that the unit for molarity is moles for every 1 liter. So you would not, if you're calculating for molarity, you would not take that 5 liters if you knew the molarity and placed it on the bottom, because now that's changing your per liter into 5 liters, which is not very good. But if we know this, we would never place that 500 milliliters below the 3.33. Keeping in mind that 3.33 big M represents 3.33 moles for every single liter. Keep that in mind, because what you're going to do is we want to get rid of the unit volume here. We're not trying to find molarity. We're trying to get rid of that unit volume so that we can answer the question and find out the mass. So again, if you know the volume and the molarity, always start with the volume. So we have 500 milliliters. And what we want to do is convert the milliliters into liters. So 1 liter is equal to 1,000 milliliters. Okay, so right now we have our liters. Now we're getting ready to move that unit diagonally. So I'm going to put my 3.33 moles right there, and my liters are right there. So ideally, my units for volume, gone. Now I can answer the question by calculating for the mass by going an additional step, moving that unit volume right down here. And then all I have to do is plug in for my mass. And I found the mass for the sodium acetate on top. That wasn't by accident. So 82.034. And then what we have is our unit moles cancel out, and we're left with grams, which is mass. So let's calculate that. So 137 grams is what we would find in 500 milliliters or a half a liter of a 3.33 molar solution. Nice. Number 20, determine the percent by mass for a solute in a solution containing 500 grams of the solute placed into 753 grams of water, creating a solution with a total mass of 1,253 grams. Now hopefully you were able to do the quick mental math and say, oh, 500 plus 753 gives me 1253. This makes that problem really fast and easy. So we're looking for the percent by mass of the solute. So this is our solute, 500 grams. So if we're looking for the percent of solute, pretty simple. Take your mass of your solute, divide it by the total mass of everything in the solution, because again, when you add something to a solution, the masses are additive. That mass just doesn't disappear. So we'll divide it by 1253. And since we're looking for a percent, multiply it by 100 and get a number. 39.9% So in that solution, the solute makes up 40% of the mass. That is a simple question. Again, chemistry is not difficult. It's all about problem solving. So analyze the question, read it a couple times, find out what it's asking, and then it's like, whoa, that's not so bad. 21. Which of these has the highest boiling point? Now remember, the equation that we use for boiling point looks like this. Delta T sub B is equal to I KB molality. Okay? Keep in mind, what we're looking for is the highest boiling point. And the nice thing is all these are 1 molar. So that means that our M doesn't change. Well, if it's the boiling point elevation that we're looking at, then the K doesn't change either. So what this is saying is that all those have the same molality, they're using the same constant, so now we have to focus on the I, or the multiplier. Recall that only ionic solutions will dissociate or break apart into smaller particles. It's not the size of the molecule, it's how many particles it can dissociate into. So if you have this sugar that has carbon, hydrogen, and oxygen in it, if I look at the value for I, what would that value be equal to? Hopefully you're saying that I, in this case, is equal to 1. So that one's probably not going to be our winner here. Looking at this one, the lithium carbonate. So I'm actually going to draw up here lithium carbonate. If that breaks apart, we're going to form 2 lithium ions and a carbonate ion. So what's my I value for lithium carbonate? I have 2 lithiums plus 1 carbonate, so 2 plus 1 is 3. So in this case, my I value is equal to 3. Well, that takes this one out of contention, so A's out. Let's look at this one. Again, we have lithium acetate. Acetate is a polyatomic. This polyatomic ion does not break apart. The lithium is 1 particle, the acetate is a 2nd particle. So in this case, the I value is equal to 2. So C is out. Looking at D, it says we have an aqueous solution of lithium nitrate. There's another polyatomic. So in this case, the nitrate doesn't break apart. It's a 1-to-1, so that means that the value for I in this case is also 2, which means that D is out. Pure water doesn't even have an I value or a molality. Pure water boils at 100 degrees. So all of these are going to boil at a much higher temperature than pure water. So your only option is B, because its I value is the greatest, while all others are the same. Love that concept. Number 22. Calculate the new boiling point for water when 3 moles of the ionic compound potassium nitrate is placed in 4,550 milliliters of water. So here we go. Same equation. So delta T sub B is equal to I KB molality. Okay? First thing that we want to look at, we have an ionic compound, potassium nitrate. So let's go ahead and write that out. So potassium and whoops, got nitrate. So KNO3. So potassium has a +1 charge. Nitrate has a -1 charge. So in this case here, we're balanced as written, potassium nitrate. So my I value in this case is equal to 2. So my I is equal to 2. My K value, again, it's a constant, it's 0.51 degrees Celsius kilogram per mole. And again, that is a constant. That's provided for you, so you don't have to memorize that. And then the last step is, let's find out what our molality is. So again, molality, by definition, is equal to your moles divided by your kilograms, which we spoke about earlier. And the funny thing is, whenever we would talk about molality, we would never solve for the molality. We would just input the values and allow the units to take care of themselves and cancel out. So in this case here, we do know our kilograms. Again, 4,550 milliliters. Remember, 1 milliliter equals 1 gram. There's 1,000 grams in a kilogram. So this actually is equal to 4.51 0.55 kilograms. So we don't have to do anything really strenuous there. Also, I gave you this, so your moles is already done. We have 3 moles of our potassium nitrate. But if I were to give you grams of that, then we'd have to convert the grams into moles. But I was nice. I gave you the moles for this. So looking at this, the kilograms cancel, the moles cancel. What unit remains? We have degrees Celsius, which is our delta T. So then, let's find out what this value is equal to. So that gives me a value of 0.67. So my delta, delta T sub B is equal to 0.67 degrees Celsius. Not a big change, but it's enough to change it. So that's my change. So if I want to find out what my new temperature is, then I would add that value to 100 and get a new temperature, which is 100.67. And you just did that not too recently, so pretty straightforward. We like that. Number 23. Number 23 asks, determine the hydrogen concentration when a solution has a hydroxide concentration of 7.45 times 10 to the negative 4. So recall that you will have access to this equation where we have the hydrogen times the hydroxide is equal to 1.0 times 10 to the negative 14. That is a constant. That will never change. So this times this always equals that. So you know the 1.0 times 10 to the negative 14, you know one of these. Actually, it's right there, the hydroxide. So we're solving for the hydrogen. So in this case, what we're going to do is we're going to move what we know, the hydroxide, we're going to divide it on both sides. So now our new equation looks like this, where the hydrogen concentration is equal to 1.00 times 10 to the negative 14. And I'm going to divide that by my concentration that I know, or that is given, and that will be equal to 1.00 times 10 to the negative 14 divided by the 7.45 times 10 to the negative 4, and that'll give me my concentration for my hydrogen. So 1.00 times 10 to the negative 14 divided by 7.45 equals 1.34 times 10 to the negative 11. Okay? So again, don't try to do this in your head. Let your calculator do this, and be sure that your calculator can do that. In other words, make sure you can do that. So what I didn't ask, and I should have asked, is once you get this value here, does this indicate for an acidic solution or a basic solution? Well, and again, I'm asking something that wasn't asked. Remember that if your hydrogen concentration is greater than your hydroxide concentration, then you're looking at an acidic solution. Okay? If your hydroxide concentration is greater than your hydrogen concentration, then you're looking at a basic solution. So which one's bigger in this case? Is our hydroxide larger than our hydrogen? Or our hydroxide is times 10 to the negative 4, that's not too bad. But our hydrogen is times 10 to the negative 11. So in this case, the hydroxide is a greater concentration than our hydrogen, and if I were to ask, this solution is considered to be basic. But I didn't ask. Number 24. Calculate the pH of a solution with a hydrogen concentration of 7.45 times 10 to the negative 4. Remember that you will have this equation. The pH is equal to the negative log of your hydrogen concentration. So what's really nice about that is plug and chug. So we have our hydrogen concentration, so the pH is equal to negative log of 7.54 times 10 to the negative 4. And again, don't forget that negative sign there. And that gives a pH of 3.13 is your pH. And as a rule of thumb, always show 2 decimal places with your pH or your pOH value. All right, the last question. Number 25, for the following reaction, where we have this right here, identify each of the species as an acid, a base, a conjugate acid, or a conjugate base. Actually, I'm going to blow this up a little bit so you can see it. So again, you're always looking at the before and after situation here. So looking at the left side, we want to find the nonmetals that are similar. So here's a PO4, there's a PO4. Okay, so we want to make sure that we're comparing those two to each other, and then we can compare the other two to each other. H3PO4 has 3 hydrogens. The H2PO4 has 2 hydrogens. So what that means is, from going from here to here, this has lost a hydrogen. Where did it go? Well, it donated it to our water molecule. So in this case here, the hydrogen ion was donated to the water molecule. Since this donated to this, acids are donors, bases are acceptors. Okay? Notice the arrow is reversible. So let's make sure that we can go from here back to here. So for the 2 to get back to a 3, what that means is that we must donate a hydrogen here. So in this case, this is acting like an acid, but since it's on the product side, it's a conjugate acid, and this is our conjugate base. Good luck on the final. I hope this video was helpful.